Hello, thank you for joining me today to replace a silicon radar MOSFET with a gallium nitride transistor. To do that, I reach to the EPC.space website, and under the Support tab, I look for the discrete cross-reference. In this page, I click the big blue button. In this field, I can enter the part number I'm currently using. The calculator finally opens in a new tab. At the very top, I can see the system application conditions. These are the conditions at which the various transistors will be compared. The circuit on the right side shows all the important elements, starting from the pull-up and pull-down resistors for the gate driver stage, the onboard external gate resistor, while the FET is exemplified in the blue box. Voltage and current forced into the FET are dependent on the particular application or the converter topology. Designers know what are the worst case for those and can enter them into these fields. I'm now going to review these parameters and make changes to fit my particular application. VBus 50 volt and drain current 8 amps is correct, as well as duty cycle and 300 kHz switching frequency. Onboard, the gate resistor 2 ohm is also correct, while gate driver pull-up and pull-down resistors are definitely too low, and I'm gonna change them to 1 ohm. Because there are temperature-dependent parameters, the thermal system is an integral part of the calculation. Like in most space applications, just conduction cooled is modeled, and all the parameters of the thermal system can be summarized with a case to ambient thermal resistance value and an ambient temperature. In this case, 5 degrees C per watt is acceptable, while I need to rise the ambient temperature from 25 to 50 degrees C. Finally, I have to choose if this is hard switch or a soft switch application. In my case, it is hard switch. I then click Update with the same parts to keep the same recommendations. Once the calculator refreshes, I can look at the first results. In this column, I see the silicon device that I'm currently using. On the rest of the columns, there are all the recommendations from the EPC Space product line. Some of these initial values are just device characteristics. You'll notice the difference in the gate drive voltage, 12 volt for silicon, 5 volt for GaN, and some of the initial results, the gate drive loss, the package area needed on the PCB, some images of the actual package, and the calculated total power loss in the system application conditions. Here I have the chance to keep all the recommendations or start selecting some. For the purpose of my application, I want to keep only the smaller packages. So I will eliminate these last ones by clicking on the X. Scrolling down, this chart helps comparing all the different characteristics as well as the calculated power losses. Y-axis can be displayed in relative terms or in absolute values. Some of the categories can also be turned on and turned off. If I keep scrolling down, I can see the waveform calculator. These waveforms are turn-on events for both transistors, my existing one and the proposed ones. I can flip between the proposed ones through the window on the right. I can also hover over the waveforms to see specific values, as well as zooming in or zooming out. The red curve is the instantaneous power loss. The area under the red curve is the energy that is spent for every single turn on. You can see the difference between silicon and GaN by zooming in into the GaN. The area is orders of magnitude smaller. The table below is a further comparison. It starts with some parameters, which can be expanded by clicking on detailed calculation comparison, as well as some calculated switching turn on and turn off, and the power losses. What is most interesting out of this tool is that it converges to the electro-thermal equilibrium for all the parts for the given conditions, particularly RDS-on. You will notice the value of RDS-on at a certain temperature. This is the temperature that is where the device reaches steady state, and the power losses are calculated. These notes help remind what are those parameters and what are those results. You'll notice that the silicon device in this particular condition runs very close to the maximum junction temperature, as well as the smallest possible gallium nitride device. Instead, the next two options show a substantial difference with respect to junction temperature. So here I have the choice to either get a much more reliable solution or a much more price competitive solution. All these data are downloadable by hitting on this button. The very last table shows a comparison in radiation characteristics. Here I notice that there is no dependence on gate bias with respect to radiation capabilities for all the gallium nitride devices, which is a very desirable feature. Thank you for joining me today.